It's the story of the cosmos which begins 1.3 billion years back when two black holes of mass around 30 times the mass of our sun merged, creating ripples of gravity waves in the space-time fabric, changing the geometry of space-time and propagating in all directions of space. Traveling over a distance of 1.3 billion light years, this wave reached the Earth on September 14, 2015. Anything falling in the path of these gravitational waves changes its shape and size, and these waves have been detected by the LIGO and Virgo network observatory by measuring this change in the length. LIGO stands for Laser Interferometer Gravitational Wave Observatory. LIGO's interferometers are L-shaped Michelson interferometers invented in the 1880s. Mirrors at the ends of the arms reflect light in order to create an interference pattern called fringes, measured by a photodetector, revealing minute details of the objects or phenomenon being studied. Michelson model experiment was done to detect the presence of ether with an arm length of 1.3 meters. While LIGO is quite different from a typical Michelson interferometer with arms 4 kilometers long, the largest ever built. The interferometer measures the change in tiny distances produced by gravitational waves. In its simplest form, a laser beam is sent towards a partially reflecting mirror called beam splitter. The beam splits along two perpendicular paths and gets reflected by the mirrors at the 4-kilometer end and recombined to form the interference pattern. As the gravitational waves pass, the distance between the central beam splitter and the end mirrors stretches along one arm and compresses along the other. This changes the time taken by the beam to travel along the two arms, and the two beams give an interference pattern, thereby enabling the scientists to measure incredibly small changes in space. Longer arms enable it to measure the change in the distances produced by gravitational wave effects, which is 10,000 times smaller than a proton, more sensitive than any interferometer ever constructed. If LIGO's interferometers were simple Michelsons, then 4-kilometer arm would still be too short to enable the detection of gravitational waves. But it will be impractical to build an interferometer much larger than 4 kilometers. So how can LIGO possibly make the measurements it does? The problem is solved by modifying Michelson design by introducing Fabry Perot cavities. This is done by placing an additional mirror at each arm near the beam splitter 4 km from the mirror at the end of that arm. This 4 km long space comprises the Fabry Perot cavity. After entering the instrument by the beam splitter, the laser beam produced by a pre-stabilized 1064 nanometer ND-YAG laser in each arm bounces between two mirrors about 300 times before being merged with the beam from the other arm. These reflections serve two functions. First, it builds up the laser light by increasing number of photons within the interferometer, which increases LIGO's sensitivity. And secondly, it increases the distance traveled by each laser from 4 kilometers to 1200 kilometers, thereby solving the length problem. For the interferometer to work, it is necessary to increase the power as more laser photons will merge from each arm. The fringes become sharper to be measured by the photodetector. LIGO's laser first enters the interferometer at about 40 watts, but for detecting gravitational waves, it needs to operate closer to 750 kilowatts. It is practically impossible to build a 1200 kilometers long interferometer with this initial power. This is solved by power recycling mirrors which continually reflects the laser light, that has traveled through the instrument back into the interferometer and boosting the power of the laser beam inside the Fabry Perot cavities. Two other modifications that make LIGO unique and able to make the world's smallest measurements are the use of signal recycling mirrors, which enhance the signal received by the photodetector, and the LIGO's seismic isolation system, constructed with extraordinary mechanisms to damp out unwanted vibrations or noise, making it easier for scientists to only pick up vibrations caused by gravitational waves. The data observed at two locations, Hanford, Washington and Livingston, Louisiana, in the United States, exactly match and confirm the detection of gravitational waves. Having these modifications, LIGO's interferometer is known as a dual recycled Fabry Perot Michelson, but in the true sense, it is still the old Michelson interferometer.